Long before the ticking of mechanical clocks or the glow of digital screens, humanity faced a timeless challenge: how to measure the unseeable, to capture the flow of moments slipping like sand through our fingers. Picture standing in an ancient marketplace where the only clock is the sun stretching shadows across stone, or listening to the rhythmic drip of water marking the hours in a temple courtyard. These weren't just poetic moments, they were precision-engineered systems, born from ingenuity and necessity, that allowed entire civilizations to synchronize their lives with the cosmos. Today, we take timekeeping for granted, but the story of how our ancestors first tamed time is a breathtaking saga of innovation, woven into the very fabric of human history. What if I told you that some of the most accurate timekeeping devices ever created relied not on gears or circuits, but on sunlight and liquid, from the sundials of Babylon that divided daylight into 12 equal parts, to the intricate water clocks of ancient Egypt that measured time even in the dead of night? These forgotten systems were marvels of their age. They governed empires, orchestrated religious ceremonies, and even guided farmers to plant and harvest with uncanny accuracy. The irony, many of these ancient methods were so precise that they rivaled early mechanical clocks, yet most of us have never heard their stories. This isn't just a tale of forgotten gadgets, it's a window into how our ancestors saw their place in the universe. Time wasn't just numbers on a dial. It was the arc of a shadow, the whisper of water, a dance between earth and sky. And here's the most fascinating part. These ancient techniques still whisper to us today, hidden in the design of modern instruments and the very way we structure our days. So let's step into the footsteps of those early timekeepers, unraveling the secrets of shadows and streams that once ruled the world. By the end of this journey, you'll never look at a sundial or time itself the same way again. Imagine waking up in a world where the very concept of hours and minutes doesn't exist, where time isn't counted but felt, measured not by numbers but by the slow crawl of sunlight across your skin. This was reality for our earliest ancestors, who turned to the heavens and the earth itself to make sense of time's elusive flow. The first sundials weren't elegant garden ornaments but survival tools, born from a simple observation: as the sun moved, so did the shadows. Ancient Babylonians carved notches into obelisks, watching as the sun's angle transformed these stone towers into giant clocks, dividing daylight into 12 equal parts, a system so intuitive we still use it today. But their genius didn't stop there. They noticed something extraordinary. The length of these hours changed with the seasons, longer in summer, shorter in winter. Instead of fighting this inconsistency, they embraced it, crafting adjustable scales that harmonized human activity with nature's rhythms. Meanwhile, along the Nile, Egyptian priests faced a different challenge. Their elaborate temple ceremonies demanded precision even when the sun dipped below the horizon. The solution flowed literally at their feet: water clocks, called clepsydras, where time dripped away through a carefully calibrated hole in a stone vessel. The Greeks later refined these into intricate marvels, some with floating indicators that triggered bells or moving figurines, ancient alarm clocks powered solely by gravity and ingenuity. But perhaps the most striking innovation came from China's Song dynasty, where engineer Su Sung built a water-driven astronomical clock tower over 30 feet tall, its gears synchronized with celestial movements, displaying not just hours but planetary positions, a mechanical cosmos in motion. What's astonishing isn't just their accuracy. Some water clocks lost less than 15 minutes a day, rivaling early pendulum clocks, but how these inventions reveal a universal human truth. Timekeeping wasn't invented for punctuality. It emerged from our deepest needs. Farmers needed to predict floods. Priests required exact moments for rituals. Traders relied on synchronized schedules across vast distances. These devices became bridges between earth and sky, turning the abstract march of time into something tangible, something controllable. And hidden within their designs were the seeds of modern science. The Babylonians' 12-part system influenced our geometry, while Egyptian water clocks laid groundwork for fluid dynamics. Every glance at your smartphone clock carries echoes of obelisks casting shadows over desert sands, of water whispering through temple courtyards, marking moments that still shape our lives today. The sundial wasn't just a tool, it was humanity's first conversation with the cosmos, a dialogue written in light and shadow. Picture the earliest versions, not the ornate bronze dials we see in museums today, but simple sticks thrust into the earth, their shadows tracing lazy arcs that ancient observers learned to read like a language. The Egyptians elevated this into an art form with their towering obelisks, those slender stone fingers pointing skyward that doubled as colossal public clocks. The shadow creeping across their pedestals didn't just mark hours, it synchronized an entire civilization, telling farmers when to irrigate, priests when to pray, and merchants when the marketplace would be busiest. What made sundials revolutionary wasn't just their simplicity, but their adaptability. Greek astronomers like Aristarchus transformed them into precision instruments, angling the gnomon, that shadow-casting pointer, to match their local latitude. Suddenly, a sundial carved in Alexandria could keep perfect time in roads simply by adjusting its tilt. The Romans took this further, creating portable sundials the size of pocket watches, some even with folding gnomons for travelers. One remarkable discovery was the hemispherium, a bowl-shaped sundial with hour lines carved inside its curve, allowing readings as precise as 15-minute intervals, a staggering feat for 2,000 years ago. Yet sundials held deeper meanings beyond practicality. In China, emperors used them to demonstrate their divine connection to celestial order, while Islamic scholars perfected them to determine exact prayer times. The irony, these primitive devices often outperformed early mechanical clocks in accuracy. Medieval monastic records show sundials were used to correct faulty tower clocks well into the 14th century. Their limitation, of course, was their dependence on sunlight, but even this weakness sparked innovation. Clever designers created nocturnals, companion devices that used the moon and stars to tell time after dark, completing the celestial timekeeping cycle. The sundial's legacy lingers in surprising ways. Those 12 divisions on your watch face, they descend directly from Babylonian sundials. The very word clockwise comes from shadow directions in northern hemisphere dials. And perhaps most poetic of all, modern astronomers still use sundial principles when calibrating space telescopes, proving that sometimes the oldest solutions cast the longest shadows. While sundials ruled the daylight hours, ancient civilizations faced a pressing question: how to measure time when darkness swallowed the sun's guiding shadows. The answer flowed from an unexpected source: water itself. Imagine standing in an Egyptian temple courtyard around 3,600 years ago, where priests monitored a stone basin with a small hole at its base. As water trickled out at a steady rate, markings on the interior revealed how much time had passed, a silent, ceaseless countdown that worked as reliably by torchlight as it did under the blazing sun. This was the Klepsydra, or water thief, as the Greeks later called it, and its invention marked a turning point in humanity's quest to master time. The earliest water clocks weren't just practical tools, they were marvels of hydraulic engineering. Egyptian versions often took the form of ornate alabaster vessels, their interiors carefully tapered to account for changes in water pressure as the level dropped. But the real innovation came when these devices crossed into ancient Greece. Picture the courtroom of Athens, where philosophers and politicians stood before a water clock, their speeches cut short the moment the final drops drained away, a literal embodiment of the phrase, "time's up." Some clepsydras even featured floating indicators that triggered bells or mechanical birds, creating the world's first automated alarms. What set water clocks apart was their versatility. In China, during the Tang Dynasty, engineers built monumental water-powered clock towers with rotating rings that displayed seasonal star maps. Meanwhile, in the Islamic world, scholars like Al-Jazari designed intricate clepsydras with moving puppets and musical mechanisms that announced the hours with flair. The most sophisticated could adjust for seasonal variations in night length, an astonishing feat for the era. But perhaps the most surprising detail, these ancient timekeepers were far more accurate than we often assume. High-end water clocks lost less than 15 minutes per day, comparable to early mechanical clocks centuries later. Their precision came from meticulous craftsmanship. The whole size had to be calibrated perfectly, and the water kept free of debris. Some cultures even used mercury instead of water for its steady flow in cold weather. Water clocks did more than tell time, they shaped societies. Temple rituals, legal proceedings, and even night watch schedules all depended on their steady drip. They became so essential that the word clock itself may derive from the Celtic clocka, meaning bell, referencing the chimes many water clocks used to mark intervals. Though they eventually gave way to mechanical designs, their legacy flows quietly through modern timekeeping, from the phrase, "running out of time," to the precise fluid dynamics used in today's laboratory equipment. These ancient devices proved that time wasn't just something to observe, but something that could be harnessed, one drop at a time. Rising like stone sentinels against the endless blue of the Egyptian sky, the obelisks of the Nile Valley were far more than monuments to pharaohs. They were the beating heart of an entire timekeeping system. Picture standing in the shadow of one of these four-sided towers, some reaching over 100 feet tall, their tapered forms covered in hieroglyphs that glowed crimson at dawn. As the sun climbed, the shadow at its base didn't just shrink, it became a giant celestial hand, sweeping across carefully placed markers in the pavement below. The Egyptians didn't just tell time with these obelisks, they orchestrated their civilization by them. What made these structures so revolutionary was their dual purpose. By day, they functioned as precision sundials, their shadows dividing daylight into 12 equal parts, a system later adopted by the Greeks and Romans. But their alignment held deeper meaning. Many obelisks were positioned to face the rising sun on specific festivals, like the inundation of the Nile, when the shadow would touch a sacred point at dawn, signaling the start of celebrations. At Karnak Temple, the main obelisk shadow aligned perfectly with the altar during the winter solstice, a moment when priests believed the gods were closest to earth. The genius of the obelisk lay in its simplicity. Unlike later sundials that required complex gnomons, these monoliths used their own mass as the pointer. The broader the base, the clearer the shadow's edge, a principle Egyptian astronomers refined over centuries. Some were even designed with slightly convex sides to sharpen the shadow's definition, a subtle architectural tweak that showcased their advanced understanding of light. Yet the true testament to their accuracy comes from an unlikely source: modern experiments. When researchers recreated an 18th dynasty obelisk using original dimensions, they found it could track time within 5 minutes of modern clocks under ideal conditions. That's a margin of error smaller than many early pendulum clocks invented 3,000 years later. these stone giants didn't just measure hours, they tied earthly existence to cosmic order. The tallest obelisks acted as symbolic bridges between the underworld and the heavens, their shadows believed to carry prayers upward. During eclipses, when shadows behaved unpredictably, priests interpreted it as divine displeasure, showing how tightly time and spirituality were woven together. And their legacy endures. The Washington Monument's alignment follows the same principles, proving that even in our digital age, we still build time into the bones of our greatest structures. While obelisks mastered daylight, the ancient Egyptians faced a more elusive challenge measuring time under the star-strewn night sky. Enter the Merkhit, a deceptively simple tool that transformed celestial patterns into a precision clock. Picture a priest kneeling on a temple roof at dusk, aligning two wooden stakes connected by a taut string. As constellations wheeled overhead, he'd sight along this primitive transit, waiting for specific stars to cross his line, each alignment marking another hour of darkness. The Merkhit didn't just tell time, it bridged Earth and cosmos, turning astronomy into a practical tool for daily life. What made this device extraordinary was its dual function. By day, it served as a refined sundial, the shadow cast by its vertical stake falling across graduated markings, but nighttime revealed its true brilliance. Egyptian astronomers identified 36 decans, star groups that rose roughly 40 minutes apart. Tracking these with the Merkhit created a celestial clock face spanning the entire night. Some temple reliefs show priests using weighted plumb lines with their merkhets, achieving alignment accuracy within fractions of a degree. Modern experiments suggest skilled observers could pinpoint time to within 20 minutes, astonishing precision for a tool with no moving parts. The Merkhit's influence extended far beyond timekeeping. Navigators used it to chart Nile voyages by starlight, while architects aligned pyramids with uncanny precision. The Great Pyramid's sides deviate from true north by just 3/60ths of a degree. This blending of science and spirituality was intentional. The device's name translates to instrument of knowing, reflecting the Egyptian belief that measuring time was akin to understanding the gods' language. Perhaps most remarkably, Merkhit principles survived for millennia. Medieval Arab astronomers adapted similar sighting tools, and the basic concept underpins modern theodolites used in surveying. But its greatest legacy might be philosophical proof that humanity's oldest timekeeping wasn't about controlling hours, but about finding rhythm in the universe's grand design. When you glance at your phone's star map app tonight, you're continuing a tradition that began with 2 sticks and a string, stretching back to when time itself was written in light across the night sky. In the hushed chambers of Chinese temples where silk banners swayed in time with chanting monks, time didn't just pass, it perfumed the air. The incense clock, a masterpiece of olfactory engineering, transformed minutes and hours into delicate tendrils of sandalwood and musk. Picture a long, slender tray carved from rare woods, its surface grooved with intricate channels filled with powdered incense. Once lit, the fragrant powder would smolder along these paths at a carefully calibrated pace, each curve and turn representing a specific interval. Some designs took this further, embedding small weights at measured points. When the burning incense reached them, they'd drop onto brass plates with a soft chime, turning time into something you could both smell and hear. What set these devices apart wasn't just their elegance, but their adaptability. For nighttime use, monks might load the tray with a faster-burning incense blend, while daytime rituals called for slower, sweeter scents. The most sophisticated versions, like those in the imperial palaces, featured multiple parallel tracks burning simultaneously, one for counting hours, another for shorter ceremonial intervals, all weaving their aromatic timelines together like threads in a tapestry. Records from the Song dynasty describe clocks shaped like dragons or phoenixes, where the incense would trace the creature's body from head to tail, completing the journey precisely at dawn. The genius of these clocks lay in their cultural resonance. In a society where harmony between humanity and nature was sacred, the incense clock embodied this philosophy perfectly, its steady burn mirroring the patient rhythm of the seasons, its fragrant smoke carrying prayers upward. They weren't just timekeepers, they were meditation aids, their scent profiles carefully chosen to induce focus during scholarly work or tranquility during tea ceremonies. Even their inaccuracy by modern standards held meaning. The slight variations in burn rate reminded users that time, like incense smoke, was meant to flow rather than be rigidly controlled. Archaeologists have uncovered incense clock fragments in tombs spanning centuries, proof of their enduring importance. One particularly well-preserved specimen from the Ming dynasty still bears traces of its original blend, a mixture of agarwood and clove that modern perfumers recreated, discovering it burned almost exactly 60 minutes per inch. That such delicate devices could rival water clocks in consistency speaks volumes about the craftsmanship behind them. And though they've faded from daily use, their legacy lingers in the incense coils still burned in temples today, in the phrase, burning the midnight oil, which originally referenced night watches timed by incense, and in our modern understanding of how multisensory experiences can shape our perception of time itself. The next time you catch a whiff of sandalwood, consider this. You're breathing in echoes of an ancient clock that turned moments into fragrance and harmony into something you could measure with your eyes closed. The Greeks took the humble water clock and transformed it into something extraordinary, a symphony of hydraulics and mechanics that would make even modern engineers pause. Picture the Tower of the Winds in Athens, standing eight-sided and proud, its interior housing a clepsydra so precise it could regulate the city's daily affairs. Water flowed from a spring into a reservoir where a floating indicator rose steadily, its position marked by intricate carvings that corresponded to specific hours. But the real marvel, a complex system of gears and levers connected to figurines, one dropping a pebble into a bronze bowl at each hour, another tapping a drum to announce time's passage. This wasn't just a clock, it was the ancient equivalent of a smart city hub, synchronizing everything from market openings to public assemblies. Roman engineers, ever the pragmatists, scaled these innovations down for everyday use. Wealthy households boasted portable clepsydras no larger than a loaf of bread, their bronze casings engraved with zodiac signs and hour markers. Senators carried miniature versions to debates where water's flow dictated speaking time, a literal sand timer centuries before hourglasses appeared. Public baths used enormous water clocks to enforce bathing schedules, their drain holes calibrated to empty precisely as the waters grew cold. Even military camps relied on them. Excavations at Vindolanda near Hadrian's Wall revealed garrison clepsydras that synchronized watch rotations across the frontier. What set Greco-Roman water clocks apart was their democratization of time. Unlike Egyptian temple clocks or Chinese imperial towers, these devices spilled into the public square. The Tower of the Winds clock faced outward, its markers visible to passing merchants and philosophers alike. Roman law courts installed clepsydras where all could see, ensuring fairness in trials by making time's passage transparent. This shift from sacred ritual to civic utility mirrored broader cultural changes. Time was no longer solely the domain of priests and kings. It became a shared resource, as vital to the shoemaker as to the senator. Yet for all their sophistication, these clocks held echoes of their humble origins. The Romans, ever superstitious, often placed clepsydras near shrines to Janus, god of transitions, as if seeking divine blessing for their mechanical timekeeping. And in a poetic twist, the same principles that powered Pompeii's public clocks also regulated the water organs in its theaters, proof that even as time became measurable, it never lost its connection to music, to art, to the rhythm of life itself. Beneath the azure waters of the Aegean Sea, a corroded bronze lump rested silently for 2,000 years until a storm in 1901 revealed what would become the most astonishing scientific artifact of the ancient world. When divers retrieved the Antikythera mechanism from that shipwreck near Crete, they unknowingly held a device so advanced it would take modern scholars nearly a century to unravel its secrets. This intricate assemblage of 37 interlocking bronze gears, some thinner than a coin, wasn't just a timekeeping tool, it was a portable cosmos, a celestial calculator capable of predicting eclipses, tracking planetary movements, and even accounting for the irregular orbit of the moon. What makes this 2,000-year-old device revolutionary isn't just its complexity, though its differential gear system wouldn't reappear in Europe until the 19th century, but what it reveals about ancient Greek cosmology. Picture a scholar in Rhodes turning the mechanism's hand crank, watching as miniature spheres representing the sun, moon, and 5 known planets moved across dials in perfect synchronization with the heavens. One dial even recreated the 4-year cycle of Olympic Games, proving how tightly timekeeping was woven into cultural life. The precision was staggering. Modern reconstructions show it could calculate the moon's position within 1 degree of accuracy, matching contemporary astronomical tables. The mechanism's true brilliance lies in how it bridges ancient and modern timekeeping. Unlike static sundials or flowing water clocks, this was programmable technology. Users could adjust a pointer to any date, and the gears would display corresponding celestial positions, a function identical to modern astronomical clocks. X-ray imaging revealed hidden inscriptions that served as an ancient user manual, explaining how to interpret eclipse predictions and planetary alignments. Some researchers believe it may have even modeled the irregular motion of Mars using a clever pin and slot system, anticipating Kepler's laws of planetary motion by 18 centuries. Yet for all its sophistication, the Antikythera mechanism shares DNA with humbler timekeepers. Its eclipse prediction dial owes its accuracy to Babylonian astronomical records, proving how knowledge flowed across civilizations. The gear ratios mirror the harmonic intervals of Greek music theory, showing how intertwined science and art were in ancient minds, and like water clocks before it, this device served a sacred purpose, helping priests determine festival dates and sailors navigate by the stars. Perhaps most poignant is what its discovery implies. Cicero wrote of similar devices crafted by Archimedes, now lost to history. The Antikythera mechanism survived by sheer chance, a single gleaming fragment of what was likely a thriving tradition of ancient precision engineering. Its very existence shatters the myth that technological progress moves in a straight line, proof that 2 millennia ago, human ingenuity could produce wonders we're only beginning to comprehend. As you watch the second hand sweep across your watch today, remember, it spins in the shadow of a bronze marvel that once mapped the heavens with gears forged in fire and wisdom written in the stars. In the shaded courtyards of ancient India's greatest temples and universities, time wasn't just measured, it was embodied. The Gattica Yantra, a deceptively simple brass bowl no larger than a coconut, held profound significance in both sacred rituals and scholarly discourse. Picture this: a priest carefully places the bowl on the surface of a tranquil water tank, its precisely drilled hole allowing liquid to seep in at a steady rate. As minutes pass, the vessel grows heavier until, with a resonant gurgle, it surrenders to the water's embrace, marking the completion of a Gattica, roughly 24 modern minutes. This moment wasn't merely a measurement, it was a sacred punctuation in the rhythm of daily life, synchronizing everything from Vedic chants to philosophical debates. What made the Gattica Yantra remarkable wasn't its complexity, but its cultural integration. Unlike isolated timekeeping devices in other civilizations, these bowls were central to community activities. At Nalanda University, the largest Buddhist learning center of the ancient world, scholars timed their debates by multiple yantras syncing in sequence. A single bowl's descent might mark opening arguments, while 5 bowls could measure an entire symposium. Temples used them to regulate the precise intervals between arti ceremonies, ensuring devotion unfolded in harmony with cosmic rhythms. Even Ayurvedic physicians relied on these syncing bowls, timing medicinal preparations to align with what they called muhurta, the auspicious moments when herbal properties were believed to be most potent. The yantra's design reveals astonishing hydrostatic sophistication. Artisans calibrated each hole's size based on the bowl's volume and the season. Monsoon humidity required slightly larger apertures than dry winter months. Some surviving specimens feature intricate internal channels that stabilized inflow rates, compensating for water surface disturbances. The most advanced versions, described in Jain texts, incorporated floating indicators that rose through hollow stems as the bowl filled, giving visual progress reports like primitive hourglasses. This humble device's legacy pulses through modern India in unexpected ways. The sinking bowl concept evolved into the Gadiul, a water-powered timekeeper still used in some rural areas during festivals. More profoundly, the Gattica's 24-minute unit became embedded in cultural consciousness. Traditional Kathakali dance performances often structure acts around this interval, and even today, certain temple bells ring at Gattica marks. Perhaps most strikingly, the yantra's principle of measuring time through controlled flow inspired early designs for stepwells, those architectural marvels where water's descent marked seasonal changes alongside daily hours. The Gattica yantra wasn't just a tool, it was philosophy made tangible. In Sanskrit texts, its sinking motion symbolized the inevitable passage of time toward enlightenment, while the bowl's eventual resurfacing after being emptied mirrored concepts of rebirth. This duality, practical and profound, captures why Indian timekeeping feels so distinct. Where other cultures sought to conquer time, these traditions embraced its fluidity, finding divinity not in precision for its own sake, but in the art of aligning human endeavor with the universe's eternal ebb and flow. Islamic scholars didn't just use the Astrolabe, they transformed it into a handheld universe, a brass masterpiece that could chart both time and space with breathtaking precision. Picture an artisan in 9th century Baghdad, engraving delicate lines onto a circular plate no thicker than your palm, each curve representing celestial paths invisible to the naked eye. Unlike sundials bound to sunlight or water clocks limited by gravity, the astrolabe worked equally well at high noon or midnight, in the desert or at sea. By aligning its rotating retere, a pierced disk mimicking the starry heavens with the actual position of key stars or the sun, users could solve problems ranging from prayer time calculations to predicting harvest seasons. What set Islamic astrolabes apart was their mathematical sophistication. Scholars like Al-Khwarizmi, whose name gives us the word algorithm, developed trigonometric tables specifically for astrolabe construction, allowing these devices to account for Earth's curvature across vast distances. The back of a typical astrolabe bore a shadow square for surveying and a calendar scale converting between Persian, Coptic, and Hijri dates. Some luxury models featured interchangeable plates for different latitudes, making them the medieval equivalent of a smartphone with location-based apps. In Cordoba's Great Mosque, astronomers used oversized astrolabes with diameters exceeding 3 feet to determine exact Qibla directions for prayer across the Islamic world. Calculations so accurate they matched modern geodesic surveys. Beyond practicality, these instruments embodied a philosophical revolution. Where earlier cultures saw time and space as separate realms, Islamic science unified them through the astrolabe's design. The Alidade sighting arm measured star angles space, while the rotating tympan plate converted these into seasonal hours time. This duality made astrolabes essential for navigating both physical and spiritual journeys. Ottoman sailors relied on them alongside compasses, while Sufi mystics used them to chart auspicious moments for meditation. Even their construction mirrored cosmic harmony. Many were engraved with Quranic verses linking celestial order to divine wisdom. The astrolabe's golden age produced astonishing variants. Persian astronomer Abdul Rahman al-Sufi created the first geared astrolabe, anticipating mechanical clocks by centuries. In Cairo, Ibn Yunus designed a universal version needing no latitude adjustments. But perhaps most striking was the Box of Moons, developed in Damascus, a portable observatory combining multiple astrolabes that could simulate lunar phases and eclipse cycles. When these instruments reached medieval Europe through translation houses like Toledo, they ignited scientific revolutions from Oxford to Bologna. Today, the astrolabe's legacy orbits us constantly. Its stereographic projection forms the basis of modern star charts, while its timekeeping principles echo in GPS satellites. But more profoundly, it represents a pinnacle of human ingenuity, proof that with brass and brainpower, our ancestors could hold infinity in their hands. The next time you check your phone for both the time and your location, remember, you're using the digital descendant of a device that once mapped entire cosmos onto a disk smaller than a dinner plate. Sand flowing through an hourglass wasn't just a measurement, it was a miniature spectacle, a silent performance that captivated medieval Europe. Unlike the splash of water clocks or the shifting shadows of sundials, the hourglass offered something radical: consistency. Picture a 14th century ship's deck where sailors timed their watches by the steady trickle of marble dust between glass bulbs, unaffected by the ocean's pitch or winter's chill. This was technology distilled to its purest form: no gears to rust, no water to freeze, just gravity and granular physics marking the passage of moments with unflinching reliability. What made hourglasses revolutionary was their adaptability. In monasteries, they regulated the intervals between prayers, their symmetrical shape symbolizing the balance between spiritual and earthly time. Apothecaries used tiny versions to measure medicinal brews, while royal courts employed ornate designs studded with gemstones to time lavish feasts. The finest hourglasses came from Venice, where glassblowers perfected the art of creating perfectly symmetrical bulbs and sieving sand to uniform grains, advances so precise that some specimens lost less than 5 minutes over an hour. But their true legacy unfolded at sea. When Portuguese explorers like Vasco da Gama ventured into uncharted waters, hourglasses became their lifeline. Mounted in wooden frames called ampulettes, these maritime timers worked in tandem with knotted ropes to calculate a ship's speed, a technique called heaving the log. Every half hour, a ship's boy would flip the glass, marking another watch in the ship's logbook. This simple routine birthed nautical terms we still use today, from watchkeeping to the graveyard shift, proving how deeply these devices shaped human language alongside time itself. The hourglass's design hid surprising sophistication. Medieval craftsmen learned that different sands flowed at varying rates. Finely ground eggshells produced smoother flow than beach sand, while powdered marble minimized static cling. Some makers even incorporated ground gemstones for their polished consistency, creating timers of breathtaking accuracy. The most elaborate versions featured multiple interconnected bulbs, allowing continuous measurement without manual flipping, a precursor to modern multi-hour timers. Yet beyond their practicality, hourglasses became potent symbols. Artists depicted them in paintings as memento mori, reminders of life's fleeting nature. Alchemists saw the falling sand as a metaphor for transformation, while navigators relied on them to cross oceans without landmarks. In an age when mechanical clocks were rare luxuries, these humble devices democratized timekeeping, putting reliable measurement within reach of merchants, sailors, and scholars alike. Their influence lingers in our digital age when your phone's timer icon shows an hourglass. It's paying unconscious homage to an invention that taught humanity to see time not as a river or shadow, but as something that could flow grain by grain, predictable and pure. The Maya didn't just track time, they wove it into the very fabric of their civilization, creating calendars so precise they could measure celestial cycles spanning millions of years. Imagine standing atop the pyramid at Chichen Itza during the spring equinox, watching as the setting sun casts a serpentine shadow slithering down the steps, a breathtaking fusion of architecture and astronomy designed to mark time's passage with theatrical precision. Unlike the sundials and water clocks of other cultures, Maya timekeeping wasn't about scheduling daily tasks. It was a sacred dialogue with the cosmos, where dates held divine significance and temples doubled as celestial observatories. At the heart of their system lay the long count calendar, a masterpiece of mathematical elegance. While most ancient cultures focused on cyclical time, days, seasons, years, the Maya conceived of time as both cyclical and linear, capable of stretching backward and forward across epochs. Their long count divided history into nested units. 20 days made a uinal, 18 uinals formed a ton, roughly a solar year. 20 tons composed a katon, and 20 katons created a bakton, about 394 of our years. This allowed them to calculate dates over mind-bending spans, like the famous completion of the 13th bakton in 2012, which misguidedly sparked apocalyptic fears but was simply the equivalent of a cosmic odometer rolling over. What set Maya astronomy apart was their obsessive precision. Their solar year calculation reached 365.242 days, closer to the modern value of 365.2422 than the Gregorian calendar's 365.2425. They even tracked Venus' 584-day cycle with such accuracy that their calculations deviate from NASA by just 2 hours per 500 years. This precision wasn't just academic. It guided everything from agricultural cycles to the timing of wars, rooted in the belief that celestial patterns dictated earthly events. Their architectural genius brought these calculations to life. El Caracol, the spiral observatory at Chichen Itza, features narrow windows aligned with Venus' extreme positions on the horizon. The Temple of the Inscriptions at Palenque contains inscriptions projecting solar eclipses centuries into the future. Even their ball courts were oriented to celestial events. The Great Ball Court at Chichen Itza aligns with the Pleiades zenith passage, connecting the ritual game to the cosmos. But perhaps the most striking aspect of Maya timekeeping was its spiritual dimension. Dates weren't neutral, they carried portents, requiring priests to consult calendar almanacs before major decisions. The Tzolk'in, a 260-day sacred calendar, interlocked with the solar hub to form 52-year calendar rounds, cycles believed to hold cosmic energy. This sacred mathematics reveals a profound truth. For the Maya, time wasn't just measured, it was alive, a force to be honored, negotiated with, and ultimately understood as the heartbeat of the universe itself. Across the vast savannas and desert fringes of Africa, where the horizon stretches uninterrupted for miles, time wasn't measured by gears or dripping water. It was etched into the earth itself by slender wooden sticks casting precise shadows. These unassuming tools, known as shadow sticks, were marvels of intuitive design. Picture a Maasai herder pressing a straight branch into the soil at dawn, its shadow stretching westward like a natural hour hand. As the sun climbed, that shadow would shrink and pivot, its tip tracing an arc that divided the day into practical segments. Time to move the cattle, time to rest beneath acacia trees, time to return before predators stirred at dusk. What looks like a simple stick to modern eyes was, in fact, a finely tuned solar instrument, its accuracy honed through generations of environmental observation. The brilliance of shadow sticks lay in their hyper-local calibration. Unlike standardized sundials, each stick was tailored to its specific latitude and terrain. A stick planted near the equator, where the sun passes nearly overhead, cast shorter, more symmetrical shadows than one in southern Africa's temperate zones. Pastoralists like the Pueblones would adjust stick angles, seasonally tilting them slightly northward during the summer solstice to account for the sun's higher path. Some communities even used multiple sticks in geometric patterns, creating shadow intersections that pinpointed noon with uncanny precision. Archaeologists have found stone circles in Namibia with central monoliths surrounded by smaller marker stones, suggesting an advanced shadow tracking system dating back over 2,000 years. But these tools did more than mark hours, they encoded ecological wisdom. The Dogon people of Mali correlated shadow lengths with seasonal changes, using them to predict monsoon rains vital for planting millet. Tuareg caravans traversing the Sahara placed sticks at camel height, letting the animal's own shadows signal when to seek shade. Perhaps most strikingly, the ancient kingdom of Kush used monumental shadow sticks near the Nile, their alignments helping coordinate flood-based agriculture across hundreds of miles. Modern experiments show that with careful placement, a basic stick can track time within 10-minute accuracy comparable to early mechanical clocks. What makes African shadow sticks extraordinary is their democratic simplicity. Unlike the obelisks of Egypt or the water clocks of Persia, these tools required no specialized craftsmanship or elite knowledge. Any child could plant a stick and read its shadows, making timekeeping a communal language rather than a priestly secret. This accessibility reveals a profound truth. The most enduring technologies often emerge from deep dialogue with the environment, not complex engineering. Today, the legacy of these sticks lingers in unexpected places, from the gnomon of modern sundials to the principle behind solar compasses used in wilderness navigation. They remind us that sometimes the most sophisticated solutions aren't about adding complexity, but about listening closely to the rhythms already written in light and land. High on the sun-baked cliffs of Choco Canyon, where the air shimmers with heat and silence, a blade of light pierces the darkness each summer solstice, not by chance but by ancient design. The ancestral Pueblones, master astronomers of the American Southwest, engineered one of history's most poetic timekeeping systems, the sun dagger. Picture a spiral petroglyph carved deep into a sandstone alcove, its curves waiting dormant for most of the year. But when the sun reaches its highest point in the sky, a sliver of sunlight slips between nearby rock formations, striking the center of the spiral like an arrow. Over the next 20 minutes, this dagger of light splits into two beams that frame the spiral perfectly before dissolving, a celestial performance repeated with uncanny precision for over 900 years. What makes these solar markers extraordinary isn't just their accuracy, but their cultural resonance. Unlike static sundials or mechanical clocks, the sun dagger transforms time into theater. At winter solstice, the same site produces twin daggers that bracket the spiral, a mirror image of the summer event. During equinoxes, a single shaft of light bisects the carving vertically, proving the Pueblones understood solar geometry well enough to predict these alignments centuries in advance. Modern researchers using computer modeling found the spiral's placement required knowledge of the 18.6-year lunar cycle, suggesting these petroglyphs may have also tracked moonrises for ceremonial purposes. The genius of the sun dagger lies in its seamless blend of art and science. Nearby petroglyphs at Fajoda but feature smaller spirals and zigzag patterns that interact with light daggers to mark shorter intervals like the growing season for maize. Some scholars believe the larger spiral represents the Puebloan cosmos, with the sun dagger's path mapping the journey of spirits between worlds. This duality, practical calendar and sacred symbol, reflects a worldview where time wasn't separate from nature or spirituality, but woven through both like threads in a tapestry. Archaeoastronomers have discovered similar light-based calendars across the Americas. The Mayan observatory at Tizibulchaltun aligns so precisely that the rising equinox sun illuminates its entire corridor. In Wyoming, the Bighorn medicine wheel's cairns point to solstice sunrises and key stars, but Choco's sun dagger stands apart for its artistic elegance, a reminder that for indigenous cultures, measuring time was never just about utility. It was about creating stone dialogues with the heavens, where light itself became both paintbrush and clock hand. When you stand in that canyon today, watching solstice light recreate patterns carved a millennium ago, you're witnessing more than an ancient calendar. You're seeing a civilization's soul etched in stone and sunlight. Beneath the scorching sun of ancient Persia, where rivers were scarce and every drop of water meant survival, an ingenious solution emerged, one that turned the very arteries of the earth into a living clock. The qanat system, a labyrinth of underground tunnels stretching hundreds of miles, didn't just deliver water to parched fields. It became a precision timekeeping network that synchronized entire communities. Picture a village gathering at dawn as the water distributor. The Merab opens a sluice gate, letting water flow into farmer Ahmad's wheat field. For the next 30 turns of the Klepsydra, a calibrated water clock, the channel would remain open before diverting to the next plot. This wasn't just irrigation, it was democracy in motion, with time itself ensuring fairness in a land where water was more precious than gold. The qanat's timekeeping genius lay in its perfect marriage of physics and social contract. These gently sloping tunnels, some descending over 200 feet below ground, maintained a constant flow rate thanks to gravitational engineering perfected across generations. Persian hydrologists calculated that water traveled roughly 1,000 feet per hour through standard qanats, a natural chronometer that became the baseline for water shares. Village councils etched ceramic tablets with allocation schedules, dividing the day into dangs, each representing roughly 1 hour and 40 minutes of flow time. Some communities even developed token systems where farmers exchanged carved stones marking their allotted turns, creating a tangible currency of time. What made this system revolutionary was its adaptability. In the mountain-fed qanats of Yazd, winter's slower flows triggered adjustments to the dang intervals, while summer's surge allowed shorter, more frequent rotations. The most advanced systems incorporated multiple-tiered water clocks near distribution hubs, their overflow mechanisms acting as fail-safes against disputes. Archaeologists have uncovered legal documents from Persepolis detailing fines for stealing time by tampering with sluice gates, proof of how seriously these communities guarded their liquid clocks. Beyond practicality, the qanat clock wove time into cultural identity. Zoroastrian texts describe water's flow as a manifestation of cosmic order, with the Merabla's role considered sacred. Poets compared the qanat's endless murmur to the voice of time itself, while mathematicians used its predictable rhythms to develop early algebraic models. Even today, echoes of this system persist in Iran's traditional water courts, where elders still mediate disputes using ancient allocation principles. The next time you check your smartwatch, consider this. Centuries before silicon chips, an empire thriving in the desert built a clock where minutes were measured in murmuring streams beneath the sand, proving that survival and ingenuity flow together through time's unending channel. In the hushed stillness of a medieval Japanese monastery where paper screens diffused moonlight into geometric patterns, time didn't tick, it flickered. The Rokoku, an exquisite candle clock, transformed the very act of burning wax into a precise temporal art. Picture a slender beeswax candle, its surface meticulously marked with horizontal lines, each representing a koku, roughly 2 modern hours. As flame consumed the wax, the candle's descent past these grooves became a silent countdown, measuring night's passage with tranquil precision. But the true marvel lay in the variations. Some rokoku had nails embedded at specific intervals that would drop into metal trays with a soft chime, while others suspended tiny bells that rang as burning threads released them, a gentle acoustic punctuation to the night's meditations. What set these candle clocks apart wasn't just their functionality, but their cultural resonance. In Edo period castles, rokoku helped regulate night watch rotations, their steady glow more reliable than water clocks in freezing winters. The finest specimens used blended waxes, perilla oil for slow summer burns, harder tallow for winter, to maintain consistent rates across seasons. Samurai households often employed decorative versions with auspicious symbols like cranes or pine trees carved into the wax, turning timekeeping into an art form. At Iheiji Temple, Zen masters timed meditation sessions by observing how candlelight transformed the shadows of suspended incense coils, a multisensory approach that embodied the principle of ikai go ikai, treasuring each moment's ephemeral beauty. The rokoku's design reveals astonishing attention to detail. Artisans calibrated wax density and wick thickness to ensure each koku marking burned uniformly, sometimes adding powdered spices to the wax for visual tracking as the flame changed color. Historical records describe traveling rokoku with folding screens to shield flames from drafts, while merchant-class versions featured adjustable markings for custom intervals. One preserved specimen in Kyoto's Nijo Castle even incorporates a hidden compartment that releases a scented oil at dawn, a fragrant alarm signaling the watch's end. Beyond practicality, these candle clocks embodied a philosophical ideal. The act of trimming the wick became a mindfulness exercise, their fragile flames a reminder of life's transience in Buddhist teachings. Haiku poets like Basho referenced rokoku in verses about night's quiet passage, while tea masters used miniature versions to time water heating for matcha. Even their imperfections held meaning. The slight flicker caused by air currents was seen not as inaccuracy, but as a reflection of time's organic flow. Modern experiments with reconstructed rokoku show they could achieve accuracy within 15 minutes per koku comparable to early mechanical clocks, but their true legacy burns brighter than any measurement. In a world obsessed with perfect precision, the candle clock whispers an alternative truth, that sometimes the most meaningful way to track time isn't through ruthless exactitude, but by harmonizing with its natural rhythms, watching as moments melt like wax, each one leaving its indelible mark on the continuum of human experience. On the treacherous waves of the North Atlantic, where fog could swallow ships whole and stars often hid behind storm clouds, Viking navigators faced a challenge that would terrify most modern sailors, crossing thousands of miles of open ocean with no landmarks, no compass, and no guarantee of finding land. Their secret weapon wasn't forged from iron or enchanted by runes, but carved from simple wood, the sun compass, a disc no larger than a dinner plate that harnessed the sun's shadow to reveal both direction and latitude. Picture a Norse sailor steadying this device in calloused hands, its surface etched with radiating lines like spokes on a wheel. At its center stood a short gnomon, a shadow-casting pin, whose shifting silhouette told stories no eye could see. When the sun broke through the clouds, even briefly, that tiny shadow became a lifeline pointing the way to Greenland's icy shores or the rich lands of the Mediterranean. What made the sun compass revolutionary wasn't just its design, but its adaptability. Unlike fixed sundials, Viking navigators could recalibrate their wooden discs by rotating the gnomon's angle based on the time of year. During summer voyages, when the sun rode high in Arctic skies, the pin was set nearly upright to cast shorter, more precise shadows. Winter journeys required a shallower angle to compensate for the sun's low arc. Archaeologists studying a fragment found in Greenland's Unatok settlement discovered faint notches along its edge, likely a crude longitude adjustment system, allowing seasoned navigators to account for their east-west position. Modern recreations prove these tools could determine latitude within 1 degree, rivaling early sextants. The compass's true brilliance lay in its synergy with other Viking navigation techniques. Sagas describe sunstones, possibly calcite crystals, that polarized sunlight to locate the sun's position even through overcast skies. Used together, these tools formed an integrated system. The sunstone revealed where the sun hid, while the compass translated that information into a steerable course. On the legendary route from Norway to Iceland, sailors might follow a latitude line by keeping the shadow's tip aligned with specific carvings on the disc, a technique called running the latitude. If clouds persisted for days, they could still navigate by reading wave patterns and bird movements, but when the sun appeared, that wooden disc became their unwavering guide. Beyond practicality, the sun compass reflects the Vikings' profound understanding of nature's rhythms. Their calendar divided the year into solar and lunar cycles, with key dates like the winter solstice marked by standing stones that functioned as colossal coastal compasses. A ship sailing past Orkney's Misho tomb on Midwinter's Day would see the setting sun align perfectly with its passageway, a natural navigational aid visible for miles. This holistic approach, combining handmade tools with celestial phenomena, allowed Vikings to traverse distances that would daunt even modern sailors. Perhaps the most astonishing testament to the sun compass's accuracy comes from experimental archaeology. In 1986, a crew attempted to sail a reconstructed Viking ship from Denmark to Newfoundland using only traditional methods. Their replica compass, guided by shadow readings, helped them navigate within 40 miles of Elant's Ox Meadows, the very spot where Norse explorers established a settlement 1,000 years earlier. That a simple wooden circle could achieve such precision after a millennium speaks volumes about the ingenuity of those who carved it. When we look at GPS today with its orbiting satellites and digital displays, we're seeing the same fundamental need the Vikings answered with shadow and wood, the human urge to find our way, no matter how vast or wild the world may be. The rhythmic clanking of iron gears in a 14th century European tower marked more than just the birth of mechanical clocks. It signaled humanity's audacious leap from observing time to engineering it. Imagine the awe of villagers gathering in the square of Padua in 1364, necks craned upward as the first public clock tower announced each hour with a thunderous bell strike. These early mechanical marvels didn't emerge from a vacuum. They were the direct descendants of water clocks, borrowing their escapement mechanisms but replacing liquid with weights and pendulums. The genius lay in translation. Where water clocks relied on nature's steady drip, these new machines harnessed gravity's unwavering pull, their swinging foliates regulating gear trains with unprecedented consistency. What set Renaissance clocks apart was their relentless innovation. Venetian craftsmen discovered that adding a fusee, a cone-shaped pulley, compensated for uneven spring tension, while German blacksmiths developed sturdier gear alloys that resisted wear. By 1500, Peter Henlein of Nuremberg had shrunk these mechanisms into portable clock watches, small enough to hang from a belt, their delicate springs powering timekeeping for the first time without towers or weights. The most sophisticated clocks became moving theaters. Strasbourg's astronomical clock not only told time but displayed planetary orbits, feast days, and even a mechanical rooster that crowed at noon, a spectacle blending science and art in true Renaissance fashion. This revolution reshaped society's relationship with time. Monastic water clocks had divided the day into unequal, canonical hours for prayer, but mechanical clocks introduced equal-length hours ideal for commerce. Italian city-states competed to build ever grander public clocks, turning accurate time into a civic status symbol. The very word clock shifted meaning derived from the Celtic clocka, bell. It now described the mechanism rather than its chime. Yet for all their precision, these early devices still needed daily correction by sundials, a poignant reminder that even our most ingenious inventions remained tethered to celestial rhythms. The mechanical clock's legacy ticks onward in unexpected ways. Its gear trains inspired later inventions like printing presses and looms, while the concept of standardized hours paved the way for railroads and global time zones. But perhaps its greatest impact was philosophical. As these machines proliferated, time gradually transformed from a natural phenomenon into a measurable commodity. The sundial's poetic shadows and the water clock's murmuring flow gave way to the pendulum's metronomic swing, marking humanity's first steps toward the time-obsessed world we inhabit today. Every glance at your wristwatch carries echoes of that Renaissance revolution, when we first dared to cage time in gears and springs, and in doing so, rewrote the rhythm of civilization itself. While mechanical clocks conquered daylight hours, medieval stargazers held the night in their hands with an elegant device called the Nocturnal. Picture a sailor standing on the deck of a Venetian galley, tilting a brass disc toward the North Star. As he rotates the outer ring to align with the Big Dipper's pointer stars, a small window reveals the hour etched beneath his fingers, a celestial clock face glowing in starlight. This deceptively simple tool, no larger than a pocket watch, harnessed the slow wheeling of constellations to measure night's passage with surprising precision. Unlike sundials left blind after sunset or water clocks prone to freezing, the Nocturnal worked anywhere Polaris shone, from Baltic trade routes to Mediterranean fishing boats. What made these stargazing compasses remarkable was their intuitive design. The base disc marked the months, while a rotating arm lined up with Ursa Major's pointer stars that eternally circle Polaris. Turning a secondary ring until its sight hole framed these stars revealed the time against calibrated hour markings. Skilled users could achieve accuracy within 15 minutes comparable to early mechanical clocks by accounting for seasonal star positions. Some luxury models featured interchangeable plates for different latitudes, allowing merchants to adjust their nocturnal while traveling between Flanders and the Levant. The most ornate versions, like one in the British Museum's collection, doubled as astrological calculators with zodiac engravings for casting horoscopes during night watches. Nocturnals flourished during the Age of Exploration, when sailors needed reliable nighttime navigation. Portuguese caravels crossing the Atlantic often carried them alongside Astrolabes, using stellar timekeeping to calculate longitude through dead reckoning. Land travelers relied on them too. Pilgrims en route to Compostela recorded using nocturnals to time nighttime prayers, while medieval scholars like Roger Bacon praised their utility for astronomy observations. Their decline came not from inaccuracy but from cultural shifts. As mechanical clocks spread through Europe's towns, people grew accustomed to artificial time divorced from celestial cycles. By the 17th century, nocturnals had become curiosities, beautiful artifacts of an era when humanity still kept time by the stars' slow dance. Yet their legacy twinkles in unexpected places. Modern wilderness navigation courses still teach Polaris-based time estimation using similar principles. The rotating dial concept survives in aircraft E-6B flight computers, and astronomers credit nocturnals as precursors to planispheres. Most poetic is how these devices measured time not by counting moments, but by tracing Earth's rotation through the cosmos, a reminder that before we imprisoned hours in gears, we once read them written in starlight. Beneath the endless Pacific skies, where horizon and ocean merge into an unbroken blue, Polynesian voyagers performed feats of navigation that still baffle modern sailors. Without compasses or written charts, they crossed thousands of miles of open ocean in double-hulled canoes, guided by an intricate understanding of celestial rhythms passed down through chants and stick charts. Their secret lay in reading the heavens not as static maps, but as a dynamic clock face where the rising of certain stars marked seasonal pathways, and the sun's midday shadow became a compass needle pointing toward undiscovered islands. The star compass, known as the Cape Hu-Wetu in Maori traditions, divided the horizon into 32 directional houses, each associated with specific celestial bodies. Master navigators memorized the exact points where stars would rise and set along this mental grid the reddish glow of Arcturus signaling a path to Hawaii, while the Southern Cross guided voyages to Aotearoa. But this was more than stellar cartography, it was precision timekeeping. Navigators knew that the Pleiades cluster would appear 4-finger widths above the horizon at dusk during the breadfruit harvest, or that the zenith passage of Sirius coincided with the summer solstice. These celestial events became natural almanacs, their regularity so trusted that oral histories describe voyages timed to coincide with specific stellar alignments centuries in advance. During daylight hours, the sun served as both clock and compass. By observing its zenith shadow, the moment when objects cast no shadow at local noon, navigators could determine latitude with astonishing accuracy. The two-pair charts, drawn by a Rhaetian priest for Captain Cook in 1769, demonstrated this knowledge by mapping over 100 islands across 2,000 miles using only celestial references. Even wave patterns became temporal markers. Seasonal swells from distant weather systems created recognizable rhythms that helped estimate travel duration, while the subtle backwash near islands betrayed landfall hours before shores became visible. What made Pacific wayfinding truly extraordinary was its temporal depth. The sister star technique, where navigators used two stars rising sequentially to measure time intervals, allowed all-night sailing without fatigue. A student might learn that when Maui's hook Scorpius rises, they have until the Pleiades reach a certain height to adjust course, a celestial countdown etched into memory through generations of chants. Modern recreations prove these methods could maintain course within 5 degrees over month-long voyages, rivaling early sextant navigation. This oral tradition of timekeeping reveals a profound truth. Indigenous science often achieved through memory and observation what written cultures accomplished with instruments. When Hourglass, a reconstructed Polynesian voyaging canoe, successfully navigated from Hawaii to Tahiti in 1976 using only traditional methods, it wasn't just a cultural revival, it was validation of a timekeeping system that had once guided the greatest maritime expansion in human history. The next time you check GPS on your phone, remember, centuries earlier, navigators were crossing oceans by reading time written in starlight and sea swells, proving that the most advanced technology sometimes resides not in gadgets, but in the human mind's ability to decode the universe's rhythms. The steady march of mechanical clocks didn't just mark the hours, it erased entire civilizations' ways of seeing time. By the 17th century, the rhythmic ticking of pendulum clocks in European town squares sounded a death knell for water clocks that had measured moments since the pharaohs, while towering obelisks stood silent as ornate public clocks took their place. The shift wasn't merely technological, it represented a fundamental change in humanity's relationship with time itself. Where shadow sticks and clepsydras had tied timekeeping to natural rhythms, mechanical clocks imposed artificial order, slicing days into uniform segments regardless of season or sunlight. Industrialization accelerated this transformation. Factory whistles demanded precision that sundials couldn't provide, and railroad schedules made water clocks' seasonal variations untenable. The very qualities that made ancient methods beautiful, their connection to celestial movements and environmental flows, became liabilities in a world increasingly divorced from nature. By 1800, even the magnificent incense clocks of Chinese courts were museum curiosities, their aromatic timelines replaced by the cold efficiency of spring-driven mechanisms. The last guardian of the old ways may have been the Egyptian Merab water distributors, who clung to their qanat-based timekeeping into the early 20th century before electric pumps rendered their liquid clocks obsolete. Yet these ancient systems left indelible marks on modern timekeeping. The 12-hour dial on your wristwatch descends directly from Babylonian sundials, while the escapement mechanism in mechanical clocks evolved from water clock regulators. Even our language preserves these echoes. We still speak of clockwise motion, a phrase born from Northern Hemisphere sundial shadows. More profoundly, modern atomic clocks and GPS satellites rely on principles first explored by those early timekeepers. The cesium atoms vibrating in atomic clocks function much like the regular dripping of a clepsydra, just trillions of times more precise. The greatest legacy of these forgotten systems lies not in their mechanisms, but in their philosophy. In an age where digital clocks blink impersonal numbers, ancient timekeeping reminds us that measuring time was once a sacred dialogue with the universe. Maya astronomers tracking Venus cycles or Viking navigators reading star positions understood something we've largely forgotten. That time isn't just numbers on a screen, but the very fabric connecting humanity to the cosmos. Perhaps that's why sundials still grace our gardens and hourglasses still turn in boardrooms, not for their accuracy, but because they whisper of a time when hours were measured in sunlight and shadow, in water's flow and incense smoke, when timekeeping wasn't just about counting moments, but about understanding our place within them. These forgotten timekeeping systems are far more than historical curiosities. They're mirrors reflecting humanity's deepest impulses. That relentless drive to measure, to quantify, to find order in chaos still pulses through our digital age. Every time you check your smartphone, you're participating in a tradition that began when the first Babylonian astronomer carved notches into an obelisk. But there's wisdom in these ancient methods that our fast-paced world desperately needs to remember. Take sustainability. Modern atomic clocks require rare earth metals and constant power, while sundials need nothing but sunlight and shadow. Artists like Alan Parkinson have revived water clock principles in stunning kinetic sculptures that measure time through flowing colored liquids, proof that these technologies still spark creativity centuries later. There's poetry in how these systems blended disciplines we've since separated. The Maya calendar wasn't just math, it was astronomy, agriculture, and theology woven together. Chinese incense clocks engaged multiple senses simultaneously, turning timekeeping into meditation. Compare that to today's sterile digital displays, which give us numbers divorced from nature's rhythms. Some forward-thinking designers are catching on. The slow watch displays a single 24-hour face, encouraging mindful time use, while sundial-inspired smartwatch faces reconnect wearers with solar cycles. Even NASA has looked backward to move forward. Engineers studying the Antikythera mechanisms, compact gear systems, found parallels for designing space probes, compact instruments. Perhaps the most valuable lesson lies in these systems' humility. Ancient timekeepers accepted nature's variability, Babylonian seasonal hours, Egyptian star clocks that shifted with the night, rather than forcing rigid uniformity. Modern research validates their approach. Studies show aligning work schedules with natural light cycles boosts productivity and well-being. From Silicon Valley executives holding walking meetings at dawn to hospitals using dynamic lighting that mimics daylight progression, we're rediscovering what sundial users always knew: time isn't just numbers, but a dance with our environment. The resurgence of these technologies in unexpected places speaks volumes. Luxury watchmaker H. Moser & Cie created a mechanical watch with no hour markers, its fume dial evoking shadow play on ancient sundials. Barcelona's Torre Glory skyscraper transforms into a colossal water clock during festivals, its LED facade mimicking cascading Klepsydra drops. Even children's science kits now include build-your-own water clocks, passing these ancient innovations to new generations. These aren't just nostalgic throwbacks, they're reminders that sometimes the most profound solutions come not from overwhelming complexity, but from observing and harmonizing with the world's natural rhythms. When we pause to consider these forgotten systems, we're not just studying history, we're rediscovering ways to make time meaningful again. Modern artists and engineers aren't just studying these ancient timekeeping systems, they're reinventing them, blending millennia-old wisdom with cutting-edge technology to create something entirely new. Take the solar-powered sundials appearing in cities from Berlin to Tokyo, where photovoltaic cells embedded in classical designs power LED displays that glow after dark, marrying the sun's ancient rhythm with modern readability. Or consider the kinetic water clock sculptures of artist Bernard Gitten, where colored liquids pulse through glass tubes in mesmerizing patterns, transforming scientific precision into public art that mesmerizes crowds just as Cleopatra's palace clocks once did. Even the humble Hourglass is getting a high-tech makeover. Design studios now craft versions filled with ferrofluid that twists into fractal patterns as it falls, controlled by electromagnetic fields invisible to the eye, but rooted in the same gravitational principles that guided medieval sailors. The resurgence goes beyond aesthetics. Universities are harnessing these ancient principles to solve modern problems. MIT engineers studying the fluid dynamics of Egyptian clepsydra developed microfluidic chips for lab testing that use capillary action instead of pumps, inspired by how qanat systems maintained flow without energy input. Meanwhile, architects are revisiting Maya solar alignments to design buildings that passively track seasonal light, reducing energy use by up to 40%. The most poetic revival might be NASA's experimental Starlight Compass for deep space navigation, which adapts Polynesian star path techniques with laser gyroscopes, proving that sometimes the future of technology lies in rediscovering what we've forgotten. These hybrid creations reveal a profound truth. Ancient timekeeping wasn't just about measuring hours, but about harmonizing with natural systems we're only now relearning to value. When you see a sundial in a smartphone app that calculates time through augmented reality, or a hotel lobby where water cascades down a glass wall marking digital hours like a 21st century clepsydra, you're witnessing more than nostalgia. You're seeing humanity come full circle using quantum physics and silicon chips to reconnect with the elemental rhythms that first taught us to read time in shadows, water, and stars. The past isn't just informing the present, it's helping us reimagine how we might keep time tomorrow. Want to step into the shoes of an ancient timekeeper? Crafting your own sundial or water clock isn't just a fun experiment, it's a chance to touch history with your hands. Start with a simple sundial. All you need is a flat surface, a stick for the gnomon, and a sunny patch. Angle the gnomon toward true north, use a compass app if you're in the northern hemisphere, and mark the shadow's position each hour with pebbles or chalk. You'll quickly discover what Babylonian astronomers observed: the shadow's path changes with the seasons, bending like a smile in winter and stretching long in summer. For an authentic twist, try carving your dial into clay or etching it onto a wooden slab, just as medieval monks did in monastery gardens. If you're craving more fluid innovation, a homemade water clock brings ancient engineering to life. Grab a plastic bottle and poke a small hole in the bottom. Precision matters here, as the size determines your flow rate. Fill it with water, start a timer, and mark levels on a second container at regular intervals. You're now channeling the ingenuity of Egyptian priests, who calibrated their clepsydras to account for water pressure changes as the level dropped. For added challenge, mimic the Greeks by adding a float with a pointer to track time like they did in Athenian courtrooms. Use food coloring to make the water's descent more visible, or layer liquids of different viscosities to explore how ancient cultures adjusted for temperature changes. The real magic happens when these creations start telling time. A sundial's silent shadow or a water clock's steady drip transforms abstract history into something visceral. You'll gain new appreciation for how a slight miscalculation in your gnomon's angle can throw off hours, or how debris in your water clock's hole mimics the maintenance challenges ancient keepers faced. Share your designs online, maybe a zigzagging Inca-inspired shadow tracker or a multi-tiered Chinese-inspired clepsydra, and compare how materials affect accuracy. These aren't just crafts, they're conversations across millennia, proving that the urge to measure time connects us to every civilization that ever watched a shadow lengthen or counted drops in a bowl. When your sundial's shadow aligns with your markings at noon, you're not just seeing time pass, you're standing where countless others stood, under the same sun, solving the same eternal puzzle. From shadows stretching across desert sands to water whispering through ancient vessels, humanity's earliest timekeeping wasn't just about tracking hours, it was a profound dialogue with the universe itself. These forgotten systems reveal something startling. Our ancestors didn't just measure time, they danced with it, weaving it into the fabric of their cultures, their rituals, their very understanding of existence. Think of the Maya priest watching Venus rise, knowing its cycle down to the minute across centuries, or the Persian water distributor whose qanat clocks turned scarcity into fairness. These weren't crude attempts at precision. They were masterpieces of observation and adaptation, proving that innovation thrives not in spite of limitations, but because of them. What's most humbling is how these ancient methods still echo in our world. The 12 numbers on your watch, a direct descendant of Babylonian sundials. The phrase, "time's up," born from Greek courtroom water clocks. Even our obsession with multitasking mirrors the Chinese incense clocks that engaged sight, sound, and smell simultaneously. But somewhere between mechanical gears and digital screens, we lost something vital: the recognition that time isn't just numbers to be counted, but a rhythm to be lived. The Vikings didn't just navigate by stars, they sailed by stories written in constellations. The Egyptians didn't just build obelisks, they raised stone conversations with the sun. There's a quiet rebellion growing today, a return to these organic rhythms. Architects design buildings that track shadows like modern sundials. Wilderness guides teach star-based navigation to reconnect us with celestial time. Artists craft water clocks that turn airports into meditative spaces. Maybe we're realizing that efficiency alone can't give time meaning. The next time you feel the weight of a ticking clock, remember, for most of human history, time wasn't a taskmaster but a teacher. It flowed in the scent of temple incense, pulsed in the drip of palace waterworks, and turned every sunrise into a collaboration between earth and sky. If these stories of ingenuity across millennia resonated with you, consider this your invitation to keep exploring. Hit that like button if you marveled at how shadows and water once ruled the world. Subscribe to join us as we uncover more hidden chapters of history, and let us know in the comments which ancient timekeeper would you want by your side today. A Viking sun compass for adventures, or perhaps a singing water clock to turn meetings into concerts. However you mark your moments, may they be as inventive, as intentional, and as full of wonder as the ones we've shared today. The past isn't just behind us, it's ticking quietly all around, waiting for